Duty cycle is a term employed to characterize the percentage of time an electrical device remains active during a specific period. Its usage extends across various electrical devices, encompassing welders, light bulbs, and motors. When considering a welder, the duty cycle signifies the duration for which the welder can operate without surpassing its temperature limits. For example, a welder exhibiting a 20% duty cycle can be utilized for 2 minutes within each 10-minute interval, ensuring it remains within safe operating temperatures. Conversely, a light bulb's duty cycle pertains to the amount of time the bulb can remain illuminated without experiencing burnout. To illustrate, a light bulb rated with a 50% duty cycle can be powered on for 5 minutes out of every 10 minutes without compromising its longevity. Generally, a device's duty cycle is established by its design and the inherent properties of the materials employed in its construction. Devices engineered with higher duty cycles typically command a higher price point compared to those with lower duty cycles, reflecting their enhanced capabilities. It's important to recognize that a device's duty cycle is distinct from its lifespan. The lifespan signifies the total operational time a device can endure before experiencing failure. In contrast, the duty cycle solely quantifies the duration for which the device can be actively employed without succumbing to overheating or other performance-related limitations. Consider a scenario involving a pulse width modulation, commonly abbreviated as PWM signal. In PWM, the duty cycle is the proportion of time a signal is in an active state versus the total time of the signal period. Expressed as a percentage, a 50% duty cycle means the signal is active for half the time and inactive for the other half. Duty cycle is essential in controlling the average power delivered to a load. For instance, if you have a 12 volts direct current supply and you are using PWM to control a motor with a 50% duty cycle, the motor will effectively receive an average of 6 volts direct current. In motor control, varying the duty cycle of a PWM signal adjusts the motor's speed. A higher duty cycle delivers more power, increasing the speed, while a low duty cycle reduces power and speed. In lighting applications, duty cycle is used to dim light-emitting diodes, commonly abbreviated as LED. By quickly switching the LED on and off with varying duty cycles, the perceived brightness can be controlled. A 10% duty cycle will result in a very dim light, while a 90% duty cycle will be almost full brightness. Consider a heating element controlled by a PWM signal. The duty cycle dictates the proportion of time the element is actively heating. A higher duty cycle results in more heat output. Duty cycle also applies to switching power supplies, which are used in numerous electronic devices to convert voltage levels efficiently. The duty cycle of the switching transistor determines the output voltage. By modulating the duty cycle, the power supply can maintain a stable output voltage even when the input voltage or load changes. When dealing with inductive loads, such as motors or solenoids, it is critical to consider the effects of duty cycle on the device's temperature. Operating an inductive load at a high duty cycle for an extended period can cause overheating and potential damage. Always refer to the manufacturer's specifications for the recommended duty cycle. In communication systems, duty cycle is relevant in time division multiple access, commonly abbreviated as TDMA schemes. Each device is assigned a time slot to transmit data, and the duty cycle refers to the proportion of time the device is actively transmitting within its allocated slot. In radio frequency applications, duty cycle refers to the proportion of time a transmitter is actively transmitting a signal. This is important for power management and interference mitigation. Selecting components with appropriate duty cycle ratings is essential for the reliability and longevity of electrical systems. When using semiconductors, such as transistors or diodes, the duty cycle affects the average power dissipation. Always check the device's datasheet for maximum duty cycle ratings at specific operating conditions. In battery-powered devices, optimizing the duty cycle of various components can significantly extend battery life. By reducing the active time of high-power consumption components, the overall energy efficiency of the device improves. When designing circuits with integrated circuits, commonly abbreviated as IC, pay attention to the recommended duty cycle ranges specified in the datasheet. Exceeding these limits can lead to malfunction or permanent damage. In power electronics, duty cycle is fundamental in controlling the operation of converters and inverters. These devices are used to convert direct current to alternating current or vice versa, and the duty cycle of the switching elements determines the output voltage and frequency. When troubleshooting electrical systems, understanding duty cycle can help identify potential issues. For example, an abnormally high duty cycle in a motor control circuit may indicate an overload condition. It is important to use appropriate measurement techniques when determining the duty cycle of a signal. Oscilloscopes and logic analyzers are commonly used for this purpose. Furthermore, it is critical to ensure that the measuring instrument is properly calibrated and configured to accurately capture the signal characteristics. Always adhere to safety precautions when working with electrical systems. High voltages and currents can be hazardous, and it is essential to use appropriate personal protective equipment and follow established safety procedures. Additionally, understanding duty cycle is valuable in the context of energy management. By optimizing the duty cycle of various electrical devices, energy consumption can be reduced, leading to cost savings and environmental benefits. When implementing control systems with microcontrollers, duty cycle is often used to regulate the output of digital to analog converters, commonly abbreviated as DAC. By varying the duty cycle of a PWM signal, a microcontroller can generate an analog voltage that can be used to control external devices. In aerospace applications, duty cycle considerations are particularly important due to the stringent reliability requirements. Components must be carefully selected and tested to ensure they can withstand the demanding operating conditions. When designing systems that involve inductive kickback, such as those with relays or solenoids, it is critical to incorporate appropriate suppression circuitry to protect against voltage spikes. The duty cycle of the switching element affects the magnitude of the kickback voltage. In automotive electronics, duty cycle is used in various control systems, including engine management, transmission control, and anti-lock braking systems, commonly abbreviated as ABS. These systems rely on precise control of electrical signals to ensure optimal performance and safety. When working with high-frequency circuits, the duty cycle of the signal can affect the signal integrity. Reflections and impedance mismatches can distort the signal waveform, leading to errors. It is crucial to use proper termination techniques to minimize these effects. In medical devices, duty cycle is a critical parameter due to the sensitive nature of the applications. Components must be carefully selected and tested to ensure they meet the stringent safety and performance requirements. When designing systems that involve thermal management, the duty cycle of the heat-generating components must be considered. A higher duty cycle results in more heat dissipation, and it is essential to provide adequate cooling to prevent overheating. In industrial automation, duty cycle is used in various control systems, including motor drives, robotics, and process control. These systems rely on precise control of electrical signals to ensure efficient and reliable operation. When working with programmable logic controllers, commonly abbreviated as PLC, duty cycle is often used to control the output of digital modules. By varying the duty cycle of a PWM signal, a PLC can generate a wide range of control signals. In renewable energy systems, such as solar and wind power, duty cycle is used to control the operation of power converters. These converters are used to convert the direct current or alternating current generated by the renewable energy source into a form that can be used by the grid or local loads. When designing systems that involve electromagnetic compatibility, commonly abbreviated as EMC, the duty cycle of the signal can affect the level of radiated emissions. It is important to use proper shielding and filtering techniques to minimize these emissions. In telecommunications, duty cycle is used in various modulation schemes, including pulse width modulation and pulse position modulation, commonly abbreviated as PPM. These schemes rely on varying the duty cycle or position of a pulse to encode information. When working with embedded systems, duty cycle is often used to control the power consumption of various peripherals. By reducing the duty cycle of infrequently used peripherals, the overall power consumption of the system can be reduced. In consumer electronics, duty cycle is used in various applications, including display backlighting, audio amplification, and motor control. These applications rely on precise control of electrical signals to ensure optimal performance and user experience. When designing systems that involve feedback control, duty cycle is often used to adjust the gain of the control loop. By varying the duty cycle of a control signal, the system can maintain stability and achieve desired performance. In scientific instrumentation, duty cycle is used in various applications, including laser control, sensor excitation, and data acquisition. These applications rely on precise control of electrical signals to ensure accurate and reliable measurements. When working with high-power circuits, the duty cycle of the switching elements must be carefully considered to prevent device failure. It is important to use components with adequate voltage and current ratings and to provide adequate cooling. In transportation systems, duty cycle is used in various control systems, including electric vehicle motor control, railway signaling, and aircraft flight control. These systems rely on precise control of electrical signals to ensure safe and efficient operation. When designing systems that involve safety-critical applications, the duty cycle of the control signals must be carefully monitored to detect potential failures. It is important to implement redundant systems and fail-safe mechanisms to ensure that the system can safely shut down in the event of a failure. In summary, understanding duty cycle is essential for designing, operating, and troubleshooting electrical systems across a wide range of applications. By considering the effects of duty cycle on device performance, reliability, and safety, engineers and technicians can ensure that electrical systems operate efficiently and effectively.